All right, guys, we are going to go over some of these textbook questions right now. So I know this chapter seems a little bit difficult, and it's not really super difficult. I think in this video I'm only going to get through half of these, and then I'll film a part two because I don't have a whole lot of time before the next class starts. Well, let's talk about question number one. Let me make sure I get my calculator ready. So it says how much work. Okay, I'm trying to find how much work or how much action I am doing. How much work is being done in lifting 100. Sorry, I'm messing up. 100-pound weight the distance of 30 inches. Okay, well, the formula for work is force, that is in pounds, multiplied by distance in feet. First thing we need to do is, look at that, we have pounds already ready to go. The more common thing to do is to put 30 inches into this formula. But 30 inches does not equal feet, obviously. So there's 12 inches in 1 foot. So what we do is we take 30 and we divide by 12, and that gives us 2.5 feet. Okay, so then we take 100 and we times it. Sorry, I'm trying to fiddle with my camera to get in the focus. We take 100 and we multiply it by 2.5. Using our little handy dandy calculator, we will get work as 250 foot-pounds, right? Pounds per foot, or foot-pounds, however you would like to write that one. And that is done. Number two says, what drawbar horsepower is required to pull a disc with a total draft of 4,000 pounds at a speed of 5 miles per hour? Here's the deal. When you hear the word draft, that equals force. Okay? Draft and force are the exact same. So, knowing that, let's collect some data right now. So what drawbar horsepower is needed to pull a disc with a total draft of 4,000? Okay, fantastic. And a speed of 5 miles per hour. So believe it or not, there is a equation for this, right? Horsepower equals force times speed divided by 375. I do not understand where the 375 came from, but when our ancestors were figuring out horsepower, that's what they figured out. Force times speed divided by 375. So let's plug this stuff in. 4,000 times 5 divided by 375. We'll go to our handy little calculator. 4,000 times 5 divided by 375. And we get a total horsepower of 53.3333 forever. 53.33. That is the answer to number 2. Move on to number 3. How fast can you pull a 10,000 load with a tractor that has 100 usable horsepower? How lucky are we that we were able to figure this one out? So let's go back. Let's see what we got. A 10,000 pound load. Okay, so that's 10,000 pounds. We got our weight. And we have a horsepower of 100. Okay, well, we need our speed. That's what we're trying to find, is speed. So it looks like we have to use this equation, right? So horsepower is 100. We are going to plug in our force, which is 10,000 pounds, and speed, which is nothing, divided by 375. There's a couple ways you can go about doing this. Me personally, I like to multiply 375 and then 375. So we get 375 equals 10,000 times speed. We divide by 10,000. And we should get our speed, which is 375. It's 3 miles, 3.75 miles per hour, which is A, because it's multiple choice on this book. Okay, let's do 2 more. Now I'm going to cut this video, and we're going to film another one. So, a tractor using 60 jar bar horsepower is pulling 18-foot tandem disc at a speed of 5 miles per hour. What is the draft per foot width of the disc? Okay, wow. There's some steps to this. 2 equations that you have to do. First, we have to figure out draft. Draft is fairly simple. It's just like your drawbar horsepower one. We're trying to find horsepower. So you take horsepower times 375 divided by speed, right? Then we need to find width. Our width is draft divided by draft per foot. Right? Nothing too crazy. But in order to get all that, we have to figure out our draft. So let's do that first. So let's see what's given. We have 60 drawbar horsepower. We also have 18-foot disc. Then we have 5 miles per hour. Fantastic. I got enough for this. So draft equals 60 times 375 divided by 5. And what do we get? Let's multiply and divide. We get a draft of 4,500. Let's plug that one in. So, we have 4,500 divided by 18. And that equals 250 pounds per foot, which is option B. Beautiful. Now, in order to do this next one, number 5, I'm going to stop at 5. In order to do this next one, we need to go to our book real quick and use some charts that are given to us. So, we go real quick. These charts are going to be your best friend for the next 4 problems. Alright, so make sure we really pay attention to these charts on here. So, this says a front wheel, let me make sure I got the right, a front wheel auxiliary drive tractor has a rating of 150 PTO horsepower. What is the maximum usable horsepower for each of the soil conditions? Now, this PTO is rated for 150 horsepower. That's not exactly the actual rating. In fact, when you fill up a tire, you're supposed to do about, depends on your tire, but you're supposed to do about half of the actual PSI. That's just maximum. You do not want, or that's just the manufacturer maximum, but what's the true usable horsepower? Right? If you go over that, your tractor can't handle it. You don't really want to go to that number because then you're really stressing your tractor out. So there is a actual maximum usable horsepower is what we call it. This might be just maximum horsepower, but it's not usable in any sort of way. So let's find it. If we go over here, look at that. We have a front wheel auxiliary driven drive tractor right here, and it gives us all of our soil types, and that's what we need to find for firm, tilled, and soft and sandy soil. So let's do that right now. So we know we have 150 PTO horsepower. Fantastic. Okay, so for firm soil, what we do is take 150 and we multiply it by this ratio. So what this says is, of that 150 horsepower, 65% of that horsepower is going to be used on firm soil. 62% of that horsepower, will be given back, I should say, on tilled soil. 55% will be given back on soft, sandy. It will make sense as I do them. I know right now you're like, what the hell is this guy even talking about? I promise it'll make sense. So let's do the first one. So 150 times 0.65. That means I have 97.5 PTO power. Okay, let's talk about tilled. 150 times 0.62, which is 93 PTO. And then on soft soil, it's 150 times 0.55, which is 82.5, PTO. Fantastic. So, these are your answers. But let's talk about why that is real quick. 97.5 PTO is very, very close. I would say very, very close to the regular PTO of a tractor. When you drive a tractor, your wheels are going to slip a little in the soil. Soil's not completely solid. In fact, even the road that you drive a car on isn't completely solid. So you're going to have a little bit of slippage. And whenever a wheel slips, that means you lost power. The looser the soil, the more your wheel slips. You may have discovered this if you ever went off-roading before and you've ever tried to driven in mud and it's so loose and slimy that your wheel doesn't have anything to grab on. So it slips. So all your horsepower that you're generating, all your punch that the car is generating is lost in this slip kind of wheel. So pay attention to that, right? And understand the looser the soil, the more the tractor is going to struggle to get up to its manufacturer maximum PTO. This max PTO is done in a controlled environment. So that is why it's kind of smaller. Cool? All right. I'm going to end this video, and we're going to start with 6 through 9.